So I call this lecture neural architecture because I'm developing sort of like an idea of how this field, this emerging field, can be described. And I borrowed the term basically from the arts and music that are using generative adversarial networks and other AI techniques, who call their productions, for example, neural music or neural art. So I borrowed that for architecture. And for architecture, we have fared fairly well when we borrow things from the arts. Neural architecture is the field of architecture that is primarily preoccupied with interrogating the emergent field of artificial neural networks as a method of designing architecture. INNs can be described in short as a sequence of mathematical algorithms which are capable of registering latent correlations in a set of data. The applied algorithms mimic certain aspects as of how the human brain operates. This position, however, is still highly disputed. As for now, and for the sake of this conversation, I would suggest agreeing that the algorithms at work in neural networks were inspired by the current knowledge about certain processes in the human brain, such as hallucinating and dreaming. In this sense, neural networks can be described as a system of neurons that can be either organic or artificial. These comprise elements of what can be described as artificial intelligence. So I run together with Sandra Manninger the architecture practice span. And I also run the newly founded, so I'm the director of the Architecture and Artificial Intelligence Laboratory at Taubman College, which was founded recently in order to expand the research we've done in the last couple of years. And I would like to start maybe with a quick run on the origins of my own practice and my obsessions. So I've been occasionally described as a member of the lineage of Viennese architects obsessed with technology. However, this obsession is not one of understanding technology as a tool of expediency, but rather the interest is in the interrogation of the tool as an agent of culture. So similar to other architects in the Austrian history, such as Koplinoblau, Hausfrucker, Hans Hollein. There's also an example here of Walter Pichler, not necessarily an architect, but certainly also within that sort of area of thinking. And that's exactly what I try to encapsulate with the projects I do together with my team. So the interrogation of contemporary culture informed by a combination of advanced technologies, theory, and philosophy. So my own history in exploring AI and machine learning started in Vienna, of course. Vienna is home to one of the world's oldest clusters of research on artificial intelligence, the OFI, the Austrian Institute of Artificial Intelligence, an offspring of the Österreichische Studiengesellschaft für Kybernetik, a registered scientific society founded in 1969. And about 30 years later, in summer 1998, Sandra Manninger and I were sitting around in a Schanigarten in the court of the Baroque ensemble that houses the OFI in the heart of Vienna. And we were discussing the possibilities of integrating artificial intelligence into architectural design with Professor Trappel, the director of the OFI, and Dr. Arthur Flexer, who you see here in a video that we recently put online, where we discussed certain ideas that came out of that research. Of course, this was a purely hypothetical conversation, since neural networks based on computational processes were in their infancy. With excitement, and of course, while sipping on a melange, they told us about a recent success back then, the simulation of one neuron to one neuron interaction. So you can imagine that that's a while ago. Some years later, in 2006, Sandra Manninger, myself, and Dr. Arthur Flexer conducted the first machine learning workshop at the Urban Strategies of the Angewandte. And then after moving to the University of Michigan, we started a collaboration with Michigan Robotics and Computer Science, which paved the way to a couple of new design techniques. And I would like to thank at this point, particularly to the director of Michigan Robotics, Jesse Grizzle, and the PhD student, Alexa Carlson, who have been crucial in this collaboration. But first, let me give you a little bit of a historical context. So the desire of us humans to attempt the imitation of thought processes with the help of synthetic matter seems to be firmly wired in our mind. There are many examples for this, but I will point out two of them. The first example is the story of the Golem of Prague, beautifully brought to the screen in the German expressionist version by Paul Wegener in 1920. A golem is an animated anthropomorphic being in Jewish folklore that is created entirely from inanimate matter, usually clay or mud. The word was used to mean an amorphous, unformed material in Psalms and medieval writing. The story goes that Rabbi Judah Leib ben Basazel used this method in 16th century Prague to create a golem to protect the population of the ghetto. What is astonishing to me is that a scroll with magic spells is placed in the golem's mouth to bring him to life, akin to programming or scripting. Language serves to bring inanimate matter to life, and of course he goes haywire. Let me give you an example that is not set in folklore or myth. And I apologize here for the poor quality of the movie, but it is too good as not to be shown. The story of the Turk is quite a fascinating one. Built in 1770 by Johann Wolfgang Ritter von Kempelen, it was designed to impress the Empress Maria Theresia. It was first displayed in summer 1770 in the Schönbrunn Palace as a chess-playing automaton and astonished the audience. On its tour through Europe, it defeated some of the time's most formidable minds, such as Benjamin Franklin, Frederick the Great, and Charles Babbage. Napoleon Bonaparte tried to cheat to win, but the Turk didn't have it and just wiped the board clean of all figures with his arm. As it toured Europe, it started to inspire more people to engage with aspects of automation and most likely triggered research on automated looms, such as in Edmund Cartwright's research, and even Babbage's difference engine. However, it was an elaborate hoax, as a person was sitting in the machine operating levers to make the Turks move. I like the idea that a Viennese hoax triggered the first modern wave in exploring artificial intelligence. And when we're talking about Babbage and the difference engine, Lady Lovelace is not far. The intimate relationship between computational processes and the human imagination emerged right there at the very beginning, when the first programmer and the first machine converged. In 1842, the ink on Lady Lovelace's seminal notes on the Turinese mathematician and scholar Luigi Menabrea and his sketch on the analytical engine was not even dry yet when she proposed that the machine could also be used to compose music. This marriage of computational tools and cultural exploration has not lost its edge to this very day. On the contrary, the emergence of artificial neural networks has infused fresh life into the conversation around the culture of machines, capable of synthetic reason. Before this potential area of cultural inquiry could be explored, the technological framework had to be created. As in so many cases, war is the mother of invention. Just in case that the Cold War turned hot, scientists were tasked to explore the potential of neural networks to perform feature recognition. Ultimately, the goal was to manage an entire array of cognitive tasks. Frank Rosenblatt was a main figure in pushing forward with inventions such as the perceptron and the concept of connectionism. And there is still this debate going on till today about the connectionism versus computationalism, which are two concepts that emerge from neuroscience. And you might already have heard that neuroscience plays a big role in the development of AI in general. The translation of basic neural patterns allowed to explore tasks such as solving mathematical problems, rudimentary translation, text creation, and feature recognition in images. These early experiments grew into what we see today. And we're talking here about like mid to late 1950s. Artificial intelligence is deeply embedded in our everyday life. Neural networks help diagnose medical cases, make decisions on bank loans, decide parole cases, read your bank checks, filter job applications, drive cars, fly drones, detect fraud, translate text, and recommend to you which book to read next. They are part of our households in the form of quasi-intelligent thermostats and security systems, help finding our way in our cars by using adaptive maps, and are close to the human body in the shape of a smartphone and watches, monitoring your moving patterns by day, your breathing patterns by night, and your heartbeat all day long in order to estimate your health status. They recognize your face and the way you type and help you photograph like a pro. Among many other things, the data generated by all these activities aid in perfecting the training of all these algorithms. In other words, AI is everywhere. However, what we currently perceive as humans of the AI ecology is just a visible part of the iceberg. The unglamorous, massive dark underbelly of artificial neural networks, providing intelligent services, managing the gargantuan amounts of data on servers, organizing the routes data takes, controlling traffic lights, managing shipping, subway schedules, and many other mundane tasks elude our field of vision. They operate, as Lev Manovich put it in his book AI Aesthetics, and I quote, in the gray everyday of the digital society, end of quote. So how does this ecology influence the production of culture? And here a little excursion on aspects of aesthetics and AI. Considering the ecology laid out in the previous section, it seems evident that the tasks designed at the dawn of the machine learning in the 1950s, such as natural speech recognition, image recognition, automated translation, and others, can be considered a smashing success. Perceptrons, adaptive linear neurons, and probabilistic reasoning paved the way for the current state of our automated ecology. However, what might be maybe less apparent than the way how artificial neural networks have become part of our everyday life is the impact that they have had on cultural production. AI has increasingly become part of the arts. In doing so, it provokes, of course, a discussion on sensibilities and aesthetics in this new field of artistic production. Just to illustrate my point, let's have a look into Mario Klingemann's work. Just one example under many, but very useful because his process is clearly laid out in a series of interviews. Simply put, a large data set of portraits from Western art ranging from the Middle Ages to around 1900 are used to train a neural network. The result is a latent traversal through the latent space of a style gun, trained on portrait paintings. Behind this technical explanation lies a strange universe of unseen but familiar paintings, softly fused heads with 4 eyes, grotesquely distorted figures in pastel tones, merging expressionist contortions with the smooth features of classicist paintings. The conventional use of style gun is continuously demonstrated by websites such as This Person Does Not Exist, which wows its audience with the capacity to create convincing realistic images. People that do, well, not exist. Could there be anything more boring than that application for such an interesting algorithm? Perfect curve fitting can produce realistic images, and in most cases of conventional AI applications, this is a desired result. However, by shying away from the perfect curve fitting, something happens, the emergence of a different aesthetics.
Machine learning, or ML, is part of applied AI, and this is actually the field, the tool sets or models we currently use in design and construction of the built environment are located. So how does this technology change the way we conceive, conceptualize, create, design, fabricate, construct, as well as maintain our built environment? How does it change the role of the architect? And how does it change the way how and what we teach? It is most certainly researched for its capacity as a tool for expedience. This is an example from research of the Technical University Munich, coming from the fields of computer vision and so-called digital twins. This machine learning model is being trained to recognize parts of the construction site, like columns or scaffolding, parts that then will be connected to a BIM model to collect projected and actual construction progress. But an ML model can also be used as a tool for surveillance, like this older example from a research project of the Hong Kong Polytechnic University from 2017, where the scientists observed individual workers' productivity. So I think this example clearly shows that we as architects have to engage in this conversation. Before we can start to look for possible scenarios, we need to get to know the individual constituent elements of this technology to be able to employ them in a way that, while using it for convenience, expedience, and service, also empower new forms of creativity and go beyond superficial forms of so-called ecological design. So what are these constituent elements? Machine learning relies on the acquisition of copious amounts of data, whereby the data can be of any form or shape. In supervised learning, this data is being labeled or tagged. So each of these sets or letters would be labeled as a 3, as an 8. For some, we would probably have problems to distinguish is this a 4 or a 7 that is actually being trained. And in unsupervised and reinforced learning, the model is trained to find hidden structures within the bulk of these data sets. So the second constituent is a mathematical model with its corresponding loss function. And it's in its simplest form, this model can be a line or curve. So in its simplest form, we see here a regression model with just a line, a linear regression model. But in most cases, it is a multidimensional surface or tensor that either needs to go as close as possible to all data points or separates them into classes. So machine learning is actually a geometrical problem. And although the mathematical models do have weights and they also have a so-called bias, the actual bias that is being discussed and criticized in the realm of ML is the bias that is generated through the acquisition of data sets. And that is exactly where we as designers and architects engage with ML. Rarely will we be choosing the specific mathematical model, at least not in the beginning, but we will be asked to collect, train, and if necessary, label the data sets the neural network will be tested on.
A couple of years ago, I had also this set of students, Hannah Dougherty, Mariana Moreira de Carvalho, and Iman Suleiman, who created a set of data sets, databases of specific architectural figures, doors, columns, stairs, variety of different things to train a neural network to create outputs. What I thought was really ingenious in this example here is what you see here, which was a class that consists of their own images, their own renderings. So the logic behind it was to test whether it's possible that a neural network can learn your own specific sensibility as a designer. This is a resulting example. For example, when you see here on the left side, one of the original renderings, and on the right side, it's a neural style transfer between their own renderings and the Baroque chapel. You might all know these examples of style transfer where you have a Van Gogh painting, you have a conventional Grachtenhaus thing here, and then you get a result that is a combination between both. I would like to point out that certain things that we learned and several other people also noticed already is that if you use similar perspectives between your style image and your target image, you get better results. Just as a side note, if you want to try it yourselves. How did we apply these ideas then in specific projects? One of the main things we did first was playing around with city maps. Satellite images seem to be particularly well fitted for this sort of experiments. And we like the idea that we can actually take historical data and understand that because we have, I think I recently tried to figure it out, we have about 7,000 years of plants. And because we have those maps and plans and this long tradition of making plans and maps, we have enormous amounts of data that we can use. And that's what we're trying to do, like including historical data in order to explore this. And the way how we achieve the data or got to the data is also maybe interesting by using scraping. Scraping is a very popular method in machine learning exercises where you have a couple of lines of code that allow you to scrape the internet for images that have specific titles. But I can also tell you from own experience that you have to be a little bit careful with what you're doing there. I think 2 years ago, we created a data set that was supposed to be about Goth architecture. And we created a scraping code that was scraping the internet for images titled Goth. Now you can imagine what you got out of that search. Like about 20% were useful. I'm gonna jump over this here. But some of those were interesting results, like for example, this one where we started to have some fun, basically speculating about cities on the moon. So this would be, for example, on a crater. And we particularly looked for 19th century science plates of the moon and Nolly maps of Barcelona, Rome, Manhattan, Washington, DC, and created these mashups between the moon and the Earth. These were entirely speculative projects at the very beginning of our research that were really helpful in grasping and understanding what these neural networks are doing, and also gave us a better understanding of how we can control it a little bit more. Although there's always the notion of, do we want to control it? The more I apply these techniques, the less I want to control them too much, because I think that the uncontrolled results are most often the more interesting ones. But that again talks more about us as humans and how we understand the world, in that they allow us to interpret things. We started with the idea of urban fictions, which instead of using vector graphics and Nolly maps, was really interested in generating something that looks a little bit more convincing as a possible city, with a variety of mashups between landscapes and urban textures. This is an example where we used an Indian landscape and Venice, or this is somewhere in China. This is Chandigarh and Vienna as a combination. And then, of course, also the idea to use your own sensibilities and specific textures, like in this case, where I used renderings of specific textures that I had designed with textures of Vienna.
Usually before we introduce these new techniques to our students, we go through our own research and apply a variety of models to different data sets. Here, a neural style transfer with pre-trained weights seemed to be quite successful for the generation of landscape and urban conditions. Again, combining it with my own or our office's sensibilities. So here, this city does not exist. It is generated by an algorithm using pre-trained weights that have learned on the famous ImageNet dataset that contains over 14 million labeled images. We were using these images to train the neural net to recognize distances between infrastructural elements, population densities, scales of subdivision or block sizes, even building heights, to integrate them later into BIM software, for example, to calculate wind loads or potential flooding.
So another method is, of course, using style GANs. This has been very popular recently, an application a lot of people have been using, because they produce really compelling results, especially if you're not training them perfectly. What I mean by that is that, specifically speaking, neural networks in general are sort of a glorified curve fitting algorithm, meaning that you have a specific curve that you want to touch on with your results so that they get realistically looking results. So you remember that example of this person does not exist. This is perfect curve fitting. So it really achieves the point where it's so close to that necessary curve to make a realistic image that it looks completely realistic. But if you move away from that curve, when you do not perfectly fit the curve, that's when interesting things happen, like the ones that you see here. So we used actually a data set of thousands of Baroque plans that we also manually deformed and mirrored, and just to increase the possible variations. You need at least 1,500 examples to get to a feasible result in a style transfer, in a neural network exercise, yeah? And then we applied that to modern plans. So we had a set with modern plans. These were some of the results we got out of that exercise. But more fascinating to me are the ones where you really move the weights of that neural network to become something different. These are the ones that are where we tweak the weights to not as close to the curve. And one of those results in further elaboration is this. And what I really like about this result is that it's a really weird result in that it has the voluptuous porches and thicknesses of Baroque buildings, but at the same time, it inherited the asymmetry of a modern building. There is like the strange visual DNA still present in this image. And you have to think about it like this, that when we could make this to perfectly emulate a Baroque plan, but as I stated before already, I don't think this is the more interesting approach to do this. But the moment where elements like estrangement, defamiliarization, ruination come into place is where they become provocative in terms of their architectural meaning for the disciplinary work, where they start to operate slightly outside of what we know, in order to provoke our mind in seeing the familiarities in it, but the estrangement at the same time.
Working with computational tools and techniques, we always use three-dimensional and generative modeling. Our work was inspired by the amazing architecture of Ray Cappy, Frank Lloyd Wright, John Lautner, other flows, or in other words, the Raum plan or space plan rather than stacked floor plans. If we wanted to integrate the quality of these architects and the ability of space into a neural network flow, we had to find different machine learning models and even more laborious create our own 3D data set. This was the first attempt, a neural renderer model developed at the University of Tokyo. It is taking a 3D mesh geometry and a style image, adds texture so creates a new mesh. It was not yet what we were looking for, but a reasonable next step in this research. And we also had a special project with a very special client. These are two of them. We had been collaborating with Michigan Robotics for a year on studio projects and paper presentations. They asked us to design a robot test ground for the multi and bipedal robots. The robot garden needs to have a series of different geological features to test the robots: sandy terrain, rocks, grass, earth, etc. We created a database with several thousand satellite images of various terrains to train a neural network to hallucinate these features on a given mesh model. In addition, we created several data sets of architectural features, such as fountains, columns, etc., and styles such as Gothic or Baroque. Playing with the weights, and we started to get a grip of how to use the technique until we got usable results. Making steps into the landscape was a requirement of the robotics lab, as well as the water feature, which will allow for flooding the robot garden to test the robots on slippery surfaces and in winter on ice. So here you can see the variety of models that we hallucinate to create features and some stills from the hallucination process. And an image from beautiful errors or glitches, that's the moment we are living for.
So deep dreaming is another technique you might have heard about. It's a very interesting technique in terms of what it does. It basically takes a target image and then applies particular features to them. And why is it doing that? Deep dreaming, you have to imagine it like this. I explained before how a neural network can learn specific features, right? So you go through a variety of layers, they learn edge recognition, feature recognition, etc. Now, what's happening here is that the flow of information is inversed. So instead of recognizing or detecting features, it tries to understand features. There's a difference in that, meaning that if it has, for example, in this case, it has a data set of lizards, birds, and feathers. And so this neural network could recognize in any photo whether there is a lizard, a bird, or a feather. And if there's nothing there, then there's nothing there. On the other hand, if you reverse the flow of information and you give this neural network an image and tell him, recognize this, what is this? Then it's going to try to make sense of the world by the knowledge that it has, which is lizards, birds, and feathers. So it's going to read those features into the given image. That's why it transforms it into this nightmarish image of Van Gogh turning into lizards, birds, and feathers. Posthuman perception of the world. You might have heard about machine learning. It's getting widely, machine vision. This is getting widely applied in automated cars, robot vision. And what you see here is such an image or an example of robot vision or machine vision based on LiDAR, light detection and ranging, which is a method that estimates the distance to objects. But that is not all. It needs to understand what is what. And for that, it uses a variety of different neural networks. One thing I'm obsessed about here is not so much the nature of the neural network, but rather the strange perception of the world that comes with it. So it seems that we're suddenly starting to share a vision of the world that is different to ourselves. And I'm really surprised how it sees palms and distance. And a thing on the left side of this image is a human figure that obviously was captured really badly. And this is actually allowing for a new way of understanding or seeing the world that is different to what we as humans are used to.
The first project we applied, the neural render model, was actually designed for the competition for the Austrian Pavilion for the Dubai Expo in 2020. It was our first successful AI-driven project. The ceiling of this project is a 2D to 3D style transfer acting between Baroque sensibilities as a style and a series of modern ceilings as the target. The result is a strangely articulated ceiling that oozes Baroque presence. The floor is intentionally kept modern to create a space full of tension between modern and Baroque sensibilities. The next work is based on a collaboration with Computer Science Michigan, who are using a powerful neural network architecture for machine learning on graphs. This was our first exploration to work directly on 3D meshes. The question was, can we collect 3D models from the hand of a designer, creating a large database of models in two distinct categories, houses and columns, in order to train a neural network to come up with additional model solutions that are generated using the learned features of the trained network. As said before, to create a design strategy that employs actual 3D geometry, we had to find the right model architecture, and we even more so generate a data set of 3D models. This is a screenshot of a geometry created for this data set containing around 1,500 labeled OBG mesh models of specific architectural classes, houses, and columns. It was the labor work of summer 2020. We refer to this data set as the sensibility data set. The next step is to train a graphic convolutional neural network on this data set to learn a mapping function between the Cartesian coordinate space of 3D models to our defined label space of sensibility features. And the next step is and the final step is to placing the trained graph convolutional neural network in an optimization framework that takes in a user-specified 3D model as input and then deforms the vertices of this model to optimize the shape of a user-specified style, aesthetics, or functionality label. So how can a neural network interrogate the inherent sensibility of a specific designer? So after our research, we can assume that we can model a designer's sensibility as a high dimensional function that can be learned from 3D models and applied to generate novel design solutions. The design technique, whose backbone is graph CNNs, is capable of modeling both the perception and creation of architectural objects. And you can read more about this project in the paper 3D Graph Convolutional Neural Networks, which we presented at Acadia in 2020.
Another project where we applied a completely different approach. Again, there's so many neural networks out there. I can tell you, like, this, for every problem, there's a neural network. So you can really, by just looking around, find incredible inspiration. And what we did here, for example, is that we used a neural network that is designed to create images out of language. I know that they have become quite popular in recent time with DALL-E and similar methods, but this was a little before those networks came out. In this case, we used an attentional neural network that we trained basically by describing parts of the architecture with language and seeing with what images it comes up with. And out of those images emerged then the entire project by using a rather simple technique of extruding volumes in order to create the entirety of this school. It was a competition in Shenzhen. We didn't win the competition, but the funny thing is that somebody saw this project and has commissioned us now to, using the same technique, do another school somewhere else in China. And he was particularly attracted by the incredible coloration. This is also very telling here in that we have a specific problem with using neural networks in architecture, in that they can either generate an interior or an exterior, but not both at the same time. And we've been trying to deal with the problem and see how we can either weaponize the problem by very specifically separating again interior from exterior, or by simplifying the interior, which we made in this case. We really created a primitively simple interior with these highly articulated exteriors, which also was, of course, was really helpful in terms of the budget for this really big school. It's a school for around 3,000 students. It has about 200,000 square meters, sorry. It would have been a nice project to build, but I'm looking forward for the school that comes next now.
So what does it mean if we are being assisted by tools that learn, when we move from using expert systems to learning systems, when we live with robots and machines, when we extend our senses through an added perception of the world? Can these tools extend our creative potentials, and will they aid us in representing scientific and mathematical concepts of space? Who will be the curator or advocate of data, the data we acquire and the data we produce? And who will be the participants in the design protocols that we are about to generate? These are the questions we discussed recently within the Neural Architecture group. Matias del Campo and I started together with Daniel Bolochan and Emmanuel Ko. And we discussed these topics also at the RD Lab, the Laboratory for Architecture and Artificial Intelligence, a collaboration with Taubman College, Michigan Robotics, and Computer Science Michigan. And I also take the opportunity to shamelessly refer to Matias del Campo's upcoming publication, Neural Architecture with Oro, that should be available end of this year. And also I have to apologize, due to the brevity of this talk, I had to leave out a lot of technical details. If you want to know more about them, there's a series of lectures and tutorial videos on our YouTube channel. And that was it. Thank you very much.